Imagine a place where gravity is king. It reigns with unimaginable power. This is the domain of black holes, the most enigmatic objects in the universe. Black holes are not empty spaces, they are cosmic monsters, incredibly dense remnants of collapsed stars. Their gravity is so strong that nothing, not even light, can escape their grasp. Black holes challenge our understanding of the universe. They push the boundaries of physics as we know it. Light, normally the fastest thing in the cosmos, cannot outrun a black hole's pull. This is why we can't see black holes directly. They are invisible to our telescopes. But don't let their darkness fool you. Black holes are far from inactive. They are dynamic forces shaping the galaxies around them. Understanding black holes is crucial to unraveling the mysteries of the universe's evolution. Join me as we journey into the heart of these cosmic wonders. Stars are the cosmic furnaces where elements are forged. They live for billions of years powered by nuclear fusion. But even stars have a lifespan. When massive stars exhaust their fuel, they meet a spectacular end. This is where the story of a black hole begins. Imagine a star much larger than our sun, at least 20 times more massive. As it runs out of fuel, its core can no longer support its own weight. Gravity takes over, collapsing the star's core in on itself. This collapse triggers a supernova, a brilliant explosion that can outshine an entire galaxy. The core, however, continues to collapse. It shrinks to an infinitesimally small point known as a singularity. This point contains the star's entire mass compressed into an infinitely small space. The singularity becomes the heart of the newly formed black hole. A black hole is not just a singularity. It is defined by an invisible boundary called the event horizon. This boundary marks the point of no return. Once something crosses the event horizon, it can never escape the black hole's gravitational pull. The size of the event horizon depends on the black hole's mass. More massive black holes have larger event horizons. Think of it like a cosmic drain. The more massive the black hole, the wider the drain and the stronger its pull. Inside the event horizon, the laws of physics as we know them break down. Space and time become intertwined. The singularity, at the very heart of the black hole, remains a mystery. We don't yet have the tools to understand what happens at this point of infinite density. Section 4. Galactic Architects, Supermassive Black Holes. While stellar mass black holes are born from dying stars, supermassive black holes lurk at the centers of galaxies. These behemoths can be millions or even billions of times more massive than our sun. Their origins are still debated, but their influence is undeniable. Supermassive black holes play a crucial role in galaxy formation and evolution. Their immense gravity holds galaxies together, influencing the orbits of stars and gas clouds. They can even trigger bursts of star formation or halt it altogether. The study of supermassive black holes provides valuable insights into the history and evolution of galaxies. By understanding these cosmic giants, we gain a deeper understanding of the universe's grand structure. Section 5. Echoes from the Abyss, Studying the Unseeable. Black holes are invisible, but their influence on their surroundings reveals their presence. Astronomers use various techniques to study these enigmatic objects. One way is by observing the motion of stars orbiting a black hole. These stars move at incredible speeds due to the black hole's intense gravity. Another method is to detect the radiation emitted by matter falling into a black hole. As gas and dust spiral towards the event horizon, they heat up and emit X-rays. By studying this radiation, astronomers can learn about the black hole's properties. Recently, gravitational wave astronomy has emerged as a powerful tool for studying black holes. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as merging black holes. Detecting these waves provides direct evidence of black hole interactions.